All right, so this is Mr. Smith here. This is Algebra 2, and we are still in section 4.6, and we're going to finish that off today. We're looking at complex number operations, and these are two warm-up problems that I asked my students to start with at the beginning of class, and so we'll go through them currently. The first one is solving an equation, and this is the thrust, this is the main idea of the entire section, is the ability to solve quadratic equations with imaginary solutions. And so we're going to solve this by trying to get this piece, the x plus 5 quantity squared piece, by itself. So first we subtract off the 12, and we get negative 8 over here. We'll divide by 2. We get x plus 5 quantity squared equals negative 4. And now take the square root on both sides. So we get x plus 5 equals positive negative square root of negative 4. And we learned how to deal with this negative square root yesterday. Right? So we got a negative underneath the square root. And so we just rewrite this as plus minus square root of 4i. And of course now we treat the square root of 4 just like a standard number, so the square root of 4 is just 2. And so we can rewrite this all as x plus 5 equals positive negative 2i. And the last step is to get the x by itself. So we subtract out the 5, and we get negative 5 plus or minus 2i. Notice again, this is a quadratic equation. This has two solutions. We obtain this using a square root method. So if you tried to factor here, factoring isn't going to work. Okay? And so let's take a look at the next problems. All right, so looking at these two problems, we want to know what is w plus y. So to add complex numbers, we simply add the real number parts. So in this case, 3 and the 4. And then we add the imaginary number parts, the 2i and the minus 3i. So if we want to know what is w plus y, we can rewrite this as 3 plus 2i plus 4 minus 3i. And again, we add the real number parts, so 3 plus 4 is 7. We add the imaginary number parts, and we get 2i minus 3i, which is minus I. Okay, so again, we look for the real number parts, 3 and the 4. We add those together to the 7. The 2i minus the 3i gives us the negative I here. Multiplication, w times y, that's a little bit more entailed. It's a little bit more difficult of a process. So this is w times y, and that equals 3 plus 2i times 4 minus 3i. And at this point, this is a binomial multiplication. We're going to multiply, some call it foiling, however you need to think of it. There will be 4 steps, 4 multiplications. So 3 times the 4, which is 12. 3 times the minus 3i, which is minus 9i. 2i times the 4, so that's plus 8i. And 2i times negative 3i, which is negative 6i squared. Okay. Now, as a review from yesterday, we looked at what I squared equals. Okay. So if you recall from yesterday, it just equals negative 1. Okay, so I'm just going to combine the like terms in the middle, and I'm going to rewrite the I squared as negative 1. Okay, so we have 12. Negative 9i plus 8i is just negative I. And then we have minus 6 times negative 1. Okay. But of course, minus 6 times negative 1 is just positive 6. Just positive 6. And so what we get is 12 plus 6. Right, 12 plus 6 is just 18. And then minus the I. So when we multiply these two guys, we get 18 minus I. Okay. So that brings us to the beginning of our new concepts. And so we're going to start off today's lesson seeing something that we've seen a little bit before, and that's the idea of a conjugate. And so if you recall, earlier in the chapter, we looked at rationalizing the denominator. So for instance, if I have 1 over 2 plus radical 3, we have a rule in mathematics that says you're not allowed to have a square root on the bottom. Not allowed to have a square root on the bottom. And so to get rid of it, we rationalize the denominator by multiplying by the conjugate. So if it was 2 plus radical 3 here, the conjugate is 2 minus radical 3. And of course, we have to do that in the top as well. Okay. And so that process, we're going to use that exact same process again, starting off in this section, except instead of having a real number here, we're going to get an imaginary number. Okay, but the conjugate idea is exactly the same, right? If I have a plus bi, then the conjugate is a minus bi. And we're going to use this, again, to rationalize the denominator. Okay, so they give you an example here. Here's 2 plus 4i. The conjugate then is 2 minus 4i. And the main advantage is I get out only a real number. Okay, so when I multiply two conjugates, when I multiply two complex conjugates, the square roots go away, the imaginary numbers go away, and all I'm left with is a real number. Okay, we're going to take advantage of that property to help us rationalize the denominator on a problem like this. Okay, so let's take a look at this guy. All right, so when we look at this problem, we have 7 plus 5i over 1 minus 4i. And the I represents a square root on the bottom, namely the square root of -1. And we have a rule in mathematics that says we're not allowed to have a square root in the bottom of a fraction. So we have to get rid of this. We have to rationalize the denominator. And again, we're going to do that by multiplying by the conjugate. So if this is 1 minus 4i, then the conjugate had better be 1 plus 4i. Exactly. Okay, and if we do that on the bottom, then we need to do that on the top. And so now, just to be clear, we don't cross-multiply. That's only when you're working with a proportion. To multiply two fractions, you just go straight across. So we multiply the bottoms, and we multiply the tops. Okay, and so we have 1 minus 4i, 1 plus 4i. And again, the reason that we're using conjugates is because the middle term should drop out, and it should leave me with only a real number. That's the whole point. If I do this and I don't get just a real number, I must have messed up. Okay, so 1 times 1 is 1. 1 times plus 4i is plus 4i. 1 times minus 4i is minus 4i. And then negative 4i times positive 4i is negative 16i squared. Careful. It's got to say I squared, because I times I is I squared. But of course, we know what I squared equals. I squared just equals -1. So what happens here is we get 1 plus 4i minus 4i. So those drop. Those two terms are gone. And then I have minus 16 times -1. So this is really just plus 16. And we get a number in the denominator here that is just 17. Okay, so now we have to figure the top out. Right, we've done the bottom. It's only a real number, so that satisfies our condition. Right, our condition said we're not allowed to have a square root in the bottom of a fraction. We've eliminated that. But now we have to figure out what goes in the top to make it equivalent. So 7 plus 5i times 1 plus 4i. And so now again we do the same process. This time the middle term shouldn't drop out. Right, so 7 times 1 is 7. 7 times 4i is 28i. 1 times 5i is plus 5i. And then 5i times 4i is plus 20i squared. Okay. So I see a 7. I have 28i plus 5i, so plus 33i. And then I have plus 20i squared. I squared is just -1. I squared is just -1. So this is really minus 20. And so then I see I have a 7. I have a minus 20. So minus 20 is -13 plus 33i. Okay, and I realize that that doesn't look much better than the original problem. That wasn't the point. The point was simply to get rid of the square root on the bottom. Okay? All our objective was to get rid of the square root that was on the bottom, and we did that by rationalizing the denominator utilizing conjugates. Okay? So at this point, why don't we try another problem, but this time you try it on your own. So if you're watching the video at home, I'd like you to pause the video at this point, and I'd like you to work on number 4, and when we resume, I'll go through the answer. So you may pause the video now. Video. Okay, so welcome back, and let's take a look here. So I see that the denominator is 3 plus I, so I'm going to multiply by the conjugate 3 minus I. So here we have that shown, and of course I have to multiply the numerator by the same thing. When figuring out the denominator, 3 plus I times 3 minus I, again, I expect the I terms to drop out. I see I have an I squared here, which is just minus 1, so minus minus 1, and we get the denominator to be 9 minus negative 1, or 10. Okay. On the numerator, 8 minus 4I times 3 minus I. Again, we go through the FOILing process, so there's 4 multiplications, and we see we get 24 minus 20I minus 4, so 24 minus 4 is just 20, and it yields 20 minus 20I for the numerator. Now for my class, I am generally very content with this answer. However, you guys should see that this actually can be broken apart a little bit farther. I wouldn't expect you to do this, but you should see how this would work. Right? So I can break this up as to 20 over 10 minus 20I over 10. Okay, so remember that both parts in the numerator are getting divided by the 10. And of course, 20 divided by 10 is 2, and 20 divided by 10 is 2. And so it would yield an answer that looks more like that. Okay. Now, this is for the purposes of maybe like an ACT. You may see something along this lines as one of your solutions, and so you'll have to take it that next step. Okay, so this section is broken up into three. This lesson is broken up into 3 parts. The first one was using the complex conjugate to rationalize the denominator. Our second piece is going to be looking at graphing complex points. Okay, so we have our idea of an XY plane. We know basically how to graph, and we are going to do that again, except instead of graphing real points, we're graphing complex numbers. Okay. And remember that every complex number is built on 2 parts. Okay. We have the A, which is the real part, and we have the BI, which is the imaginary part. Okay. We have the real part and the imaginary part. Okay. And so what we're going to do is we are going to graph using these 2 pieces of information. Okay. We're going to graph using these 2 pieces of information. So let's just jump right to it. So here's our graph. Here's our graph. And what you see, is that there are 2 axes, but we don't have an x-axis and a y-axis. See an x-axis and a y-axis. We see a real axis and an imaginary axis. Okay. Now remember, every number, this is a number, a complex number, it has 2 parts. It has a real part and it has an imaginary part. Okay. And so those are the 2 pieces of information we're going to use to graph these points. So let's just get this first one out of the way, and I think you'll find it goes a little nicer. So this is the number 3 minus 2I, and so the real part is 3. So I just go to the right 3 units. And now the imaginary part is negative 2, or negative 2I. So we go down on the imaginary axis 2 units, and that is the point A, or the number, the complex number, A. Okay, so we just take this knowledge of the real number piece, the imaginary number piece, and we use it to graph on this complex plane. Okay, so this isn't the XY plane that we're used to graphing on. It's just a different plane. It has a real axis, which was where the x's went, and we have an imaginary axis, which is where our y's went. So here I have the complex number negative 2 plus 4I. So on the real axis, I go left 2, and on the imaginary axis, I go up 4. Right, there's point B. So this shouldn't be too bad. Right, we've done a lot more complicated things this year. Now point C, that's interesting, right? It doesn't have a real number part. So class, what do you think I'm going to do? Yeah, very good. I'm not going to go, if you want, you could think of it as a 0 out front, but I'm not going to go left or right any. I'm just going to stay right on the imaginary axis. And now I'll go up 3 units. Okay, that's our point C. And lastly, point D is very similar. We'll go to the left 4. We'll go to the left 4 and then down 3. So 1, 2, 3, 4. 1, 2, 3. And there's the point D. Now, one thing to keep straight, this is a number, right? So what we're used to plotting is ordered pairs, right, that had an x piece and a y piece. So it was actually 2 numbers. In the complex plane, This is actually just one number, but we can plot it because it has two components to each number. And there's more things that you can do with graphing of complex numbers. We're not going to worry about those. Just want you to see a basic idea here. Okay? So the first idea that we covered in this chapter was rationalizing the denominator. The second one is graphing these points on the complex plane. And the third piece is calculating a complex number's absolute value. So the third piece of this section for today's lesson is calculating the absolute value of a complex number. And probably the first place you want to kind of bring your eyes is to this phrase: the absolute value is the distance, okay, so we know distance, we know how to work with that, between the point Z and the origin on the complex plane. So when I graph a point, so imagine this is the point Z right here, and if I want to find the absolute value, it's basically this hypotenuse of that triangle between A and the B. And well, just so happens we have a really good method for finding the length of a hypotenuse of a triangle. It was our old man, our old friend Pythagoras, right? He gave us this theorem, and basically this square root is the Pythagorean theorem. Okay, so the absolute value is the distance between a point on the complex plane, a number on the complex plane, and its distance between that and the origin. And the way we calculate it is by taking a squared, where a was the real number part, and we add it with b squared, which b was the complex or the imaginary number part, and we add those together, take the square root, and that is the operation that we define as the absolute value. Okay. So here we are. I have -4 plus 3i, that's a complex number. I think you would all agree with me there. And if we want to find the absolute value, we're just going to take the square root of -4 squared plus 3 squared. Okay, -4 squared plus 3 squared. Okay, so -4 squared is 16, 3 squared is 9, so this is the square root of 16 plus 9, which is the square root of 25, and the square root of 25 is just 5. Now we don't need to consider the negative case here, because we're talking about a distance, right? So there's this really nice property then about absolute values of complex numbers. Number one, you're going to get a real number, right? So I can take the absolute value of a complex or imaginary number, and I get out a real number, always. And this number will always be positive. Okay, the absolute value will also always be positive, and the reason for that, or 0. But the reason for that is because we're talking about a distance, right? So we always measure distance in positive real numbers. Okay, we can do, again, the absolute value of this -3i, so this second problem. And so we take the square root, and we square the real number part, but there is no real number part. So we could just say, well, that's 0, if you want to put it in there. And 0 squared is, of course, just 0, so that's not really interesting. And then we have the imaginary number part, which is -3. And so I square -3. And so that's going to give us basically 0 plus 9. So we're going to take the square root of 9, which is just 3. Okay. And so the absolute value of this point, -3i, is 3. And that's the answer. That's the absolute value. Notice that the I really doesn't have any part in the square root. The I doesn't come in here anywhere. Okay, so don't try to bring it in. The I is no piece of this. The other idea that I want to show you is let's think graphically about where this point -3i would be. Okay, so I'm going to go back to the graphing slide. Hang with me for just a moment. And so the point -3i should be right here, right? And remember that the absolute value, so this is the point that we're working on, the absolute value is just the distance from the origin to the point. So if I count this, 1, 2, 3, right? So for -3i, for -3i, here's our point, here's our number. The absolute value is just 3. Okay, and so you could, that's exactly right. The question was, can you just count the spaces? And that is absolutely correct. So for instance, for part B, for the number B, so this guy right here, if I want to know what the absolute value of this, negative 2 plus 4i, and I want to know the absolute value of that. Basically, it is this distance right here. And if I could count that easily, I would know what the absolute value was. Otherwise, I'll have to use Pythagorean theorem, which says, well, hey, this length is 2, this length is 4, 2 squared plus 4 squared equals c squared, and I'll take the square root there and find out what this absolute value is. Okay. So there were 3 concepts that we learned: rationalizing the denominator, graphing points on the complex plane, and then how to find the absolute value. And that's going to conclude this section, the rest of section 4.6. As a reminder, though, the key part was actually kind of the first problem that we started the day with, which is this problem here. This is the key piece to the section, in my estimation, because we're trying to solve quadratic equations. So we'll see you next time. Thanks for watching.